So hi everyone, very happy to share with you on our study, Cellular Automata as a Pedagogical Agent for Contextual AI in Ecological Architecture, a human-machine collaboration. So this is our team. We are a group of researchers from all over the world, and we focus on artificial intelligence application in bio-inspired architecture design. And we start from the problem of negotiating automation. The need to create buildings that can intelligently respond to both ecological and cultural variables is increasingly facilitated by generative algorithms. However, Gen AI that are trained on mainstream dataset possess a normative understanding of the world that could easily homogenize both our design practice and design outcomes. So this study confronts this critical tension at the forefront of sustainable architecture. How to embed contextual intelligence into automated workflows without reducing design to universalist optimization while facilitating designer creativity in the process. Our solution starts from thinking about the intersectional challenge between rule-based and machine learning systems, each demonstrating a different kind of intelligence that perhaps can complement each other in their training process. Cellular automata can model local interaction and bridge environmental specificity, including solar responses, material aggregation, and so on. However, these rule-based systems face scalability bottlenecks. For instance, it often requires hundreds of gigabytes and tens of hours for full evolutionary optimization. On the other hand, machine learning promises acceleration, but it often operates in a contextual void. For instance, the use of generative adversarial network, GANs, in architectural design often privilege stylistic translation over situated intelligence. And so our study framed this not as an algorithmic replacement, but a pedagogical collaboration. That rule-based system can help contextualize ML tasks, while ML help accelerate rule-based tasks. However, in our prior study, we encountered three critical challenges that stifle designer autonomy in this automated feedback process. These include, first, a rigid discretization that could hinder more organic forms and cultural adaptation. And also, we had inadequate control for contextual variables, including local resources and aesthetics. Finally, computational inertia in translating cellular automata states into solutions. To resolve this, we studied how recent advances in bio-inspired design synergize machine automation with human creativity. So this video was a previous test by Davi, our team member, to understand how to advance generative algorithm beyond metaphorical form finding, but operationalize as a distribution logic according to predefined input. As we can see, the ML agent is navigating a voxel grid according to that predefined input. Now, these we learned a lot from precedents also at the Bartlett School. For instance, Gilles shows how discrete aggregation of modular units can encode digital craftsmanship, leveraging a bottom-up biological intelligence as a design model. Daniel Collar presenting data aggregation as a form of cultural expression, which synthesized social ecological with topological assembly. So learning from these precedents, we reflected on how our biomimicry objectives. First, to capture into a machine learning model a design process that originally would demand prohibitive computation can be executed relatively instantaneously and test the pipeline in various design scenarios. Second, to evaluate the shift of cellular automata from a computationally heavy generator to an intelligent pedagogical tool for machine learning. And finally, to analyze how combinatorial tooling can help bridge designer intuition and machine efficiency. So from rule definition to pattern replication within an automated workflow. And we assessed the system through threefold methodology. First, we conducted experiential workshops. Then we do performance benchmark. And finally, we do conflict framing to understand the next step for the study. So we developed a 3-phase workflow. In phase 1, the rule-based tutor, which is the cell automata, simulates site constraints, for instance, solar instances, into a discrete cell states that would generate a synthetic dataset. This dataset then becomes a training protocol for our pix-to-pix GAN to accelerate the simulation in PyTorch. And finally, Houdini would dynamically recalibrate the pixels into voxels through growth algorithms and translate the simulation data into 3-dimensional data proxies. In phase 2, the cross-context deployment, we did it with 20 architects across 12 countries, working in teams of 4 through a workshop format. So each team would select a site in their local context with documented climatic and cultural constraints. And then we'll deploy the steps in phase 1 to train the AI and accelerate the design iteration for each site. Finally, we refine the outputs via human-machine feedback loops. In phase 3, we do the benchmarking, where we quantify the computational trade-offs, including CA precision versus ML speed, and storage demands, hardware scalability, etc. And then we reflect with participant the human-machine protocol in the process and reflect on the conflict for improvement in the next phase. So let's see some prelim results. We selected 2 outcomes to demonstrate how the same combinatorial pipeline can give emergence to vastly different design results. The 2 projects have very different contexts, different participant, different local organism as inspiration. And one was in the northern hemisphere, the other one in the southern hemisphere. Although both contexts are relatively close to the equator, they suffer from different climatic concern, and one was in a desert, another in highland climates. And both projects tried to hybridize active and passive solar strategies into one design, as the surrounding environments are relatively scarce in resources due to social, economic, or geographical reasons. And that we do context as curriculum. The first sample project is the Sana Refugee Tower in Yemen. So it is a low-rise refugee shelter in resource-scarce urban fabric near a mosque in Yemen, which is a port nation with a lot of discarded shipping container. So participants had the idea to upcycle the shipping container into PV integrated energy resilient blocks so it can harvest light into solar energy. However, there was a problem of how to orientate each block so then they can harvest light from all year round. And so the integrated techniques of modular integrated construction, where distribution logic should maximize site boundaries without landscape homogenization. And they went through a structured process with a combinatorial pipeline, meaning that the algorithm which we share with them, they will arrange in different sequence to achieve the design. So they first do a solar simulation that structures the CA voxel grid. Then they upsample the voxel with the container geometry so it can speed up the process. And then they identify luminescent solar concentrator as the facade of each of the units, which is an ultra low cost fluorescent window harvesting device that can maintain transparency while acting as a solar unit. And finally, they did a multi-site analysis that prioritized adjacent site to mosques, which are cultural solidarity hub in the area, that they realized that there were more mosques than supermarkets in that place. And this basically validates the pipeline that is replicable for temporary towers. The key innovation participant demonstrated was that voxel can be used as computational proxy for detailed design. They enable efficient CA to ML knowledge transfer while resolving modular integrated construction challenges in continuity of the design through designer mediation. In a second design, we can observe that it was vastly different. The first one was based on rectangular module. This one had a bit more organic form. And this was designed for a resting station in remote highland trails in Plateau Geopark within Peru. They tried to integrate spherical solar harvesting devices with shading provision. And this hybridized an active passive strategy through micro solar cells that can capture omnidirectional light, where 50% of surface exposure is captured during daytime. And this include reflected and refracted rays. And second, they will have vapor harvesting webs that can condense moisture during sunrise. The biological computational workflow first start with simulating a lichen growth in Houdini. So they flip the pipeline the other way around. And then they discretize the form into voxels for CA-driven solar training. Then they train the pix-to-pix scan with solar data, and they stack the pixel outputs into voxels again. And this reconstructed the biomimicry geometry in Houdini. So the differences in the project are not simply in the design and the aesthetic, but also in the way how computation were played to the advantage of each design. In a way, they conducted design diversification through contextualizing the AI acceleration. For instance, in a Sana Tower, because it was based in a desert climate, the CA role was to calculate solar instances that dictate the modular aggregation of container. The AI had the role to optimize the window orientation and provide diverse design options very fast, whereas the human was mainly working on voxel proxy minimized computation to articulate and resolve continuity between the units in the final outcome. Whereas in the Lycian project, because the context was in a highland with water and electricity source scarcity, the CA role was first to simulate the Lycian moisture harvesting structure, whereas the AI transformed the solar data into spherical cell arrays, and a human's job was to define the bioform discretization into voxel that would enable the CA and ML knowledge transfer. And because of how they play competition to different advantages, the key innovation were also different. In the first project, they diversify modular integrated construction method controlled by environmental inputs. In the second project, the spherical topology formalized environmental intelligence into discrete CA rules, accelerated by ML for rapid adaptive prototyping. Our benchmarking reveals that CA and ML as complementary agent in a pedagogical framework each has different advantages and disadvantages. First, the CA as a teacher employ evolutionary method to optimize design against explicit fitness function, and it thrives in low data or sensitive context, generating high fidelity, physics validated synthetic data. However, this demands severe computation, including 6 to 7 hours for 1,000 generation with 70 gigabyte storage for population data. But its strength lies in diverse multi-objective exploration, unaffected by dataset dependencies. On the other hand, the AI as the student excels in post-training tasks. Adversarial networks synthesize design within seconds. Yet the training requires structured dataset and also 8 to 10 GPU hours. It can also struggle with high resolution input. So you can see that the dataset we used was 250 times 250 pixel each. But the output quality also hinges on dataset diversity. However, the storage is relatively lean, 2 to 4 gigabytes, and we can actually design the training checkpoint to minimize training time depending on the dataset quality. So overall, they are good for different use cases. The CA is good for context with very little data to generate synthetic datasets, whereas SCAN is good for data-rich context, and it provides almost instantaneous inference. So our overall proposed synergy is that CA can handle contextual optimization, while the AI accelerate generative iteration. So finally, we theorize this observation into two terms. First is intelligence as negotiated collaboration. The workshop basically argued that automation value lies in structuring the triad of human, CA, and machine collaboration. The human should define priorities, including cultural needs and solar thresholds, whereas the CA formalizes these needs into discrete teachable rules, and AI learns and accelerates the application. But this is not simply a technological shift, but a conceptual one. First, from automation to pedagogy. That rule-based system structure contextual biases as teachable protocols for machine learning. Second, biomimicry act as an operational logic. So the bio-inspired design is not simply form finding, but aggregation of units became computational distribution rules. And finally, hybrid workflows are always necessary. The human priority steers CA, CA trains ML, and ML accelerate human creativity. In a way, the result tries to question human agency in the process, as well as algorithmic agency in the process. And this basically reflects on the tension between computation and spontaneity. Human intervention as modular input within a combinatorial pipeline can help to prevent computational bottlenecks. And this includes having discretizing continuous bioforms versus aggregating discrete units into bioforms. Second, balancing voxel resolution against computational load. And third, negotiating microscale inaccuracy in ML outputs. However, limitation persists throughout this process. The first synthetic dataset risks closed-loop detachment from real-world performance, and so in the next step, we should do physical prototype to test whether the digital design actually conform with physical performances. Second, cultural adaptation relies on designer intuition, aka tacit knowledge, and in current stage, we have insufficient understanding of how tacit knowledge actually plays a part in the computational process, and so we will also focus on that. And finally, voxel interoperability remains underdeveloped between different software spaces that designers are creative in. And so we will continue to expand that in our computational combinatorial pipeline. Finally, we would just like to highlight that the process underscore collaboration as a multi-scalar human-machine, machine-machine, and machine-machine process. And this includes translating intent to automation, from CA to ML pedagogy, and negotiating contextual diversity. Ultimately, it should highlight a tension between dynamic, self-configuring proposal and the static, perpetuate realities of build architecture. So looking at participant feedback, I think some of the quotes can be very helpful in orienting the whole project within current practices. So they think that architects base our design skills and criteria on personal learning experience, and AI does pretty much the same, with the difference that it has the capacity of choosing combinatorial paths of data. And even though the decisions were made by architects evaluated by machine to get a product, it has the opportunity to go back again in the loop, which is different from current practices. And so the future of design relies on self-configuring architecture. The architects can make accurate proposal that can adapt to the slightest environmental change per month, per day, per hour, and per minute. This basically clashes with the reality of today's architectural product that is static and perpetuates. And from the mapping, we can see how architects' design skills and algorithmic learning can be iterated into a product design, combining architects' test experiences with extensive view of machine learning processes. We conclude that the study revealed a negotiated choreography between human and synthetic intelligence, with workshop participants deploying variable workflows from initiating processes through parametric forms, manipulating data points to solar simulated voxel grids. This minimized processing labor, but it also introduced micro-scale discontinuities, which are mediated by designer in the process through either discretizing continuous form or aggregating units with connectors. We conclude that scalable intelligence in architecture is not autonomous, but collaboratively constructed. Machines must learn as students of ecological and cultural wisdoms, with architects as interpreters of computational nuance. And to tackle solutionism, homogenizing forces, we must continue to engineer frameworks for negotiating tension. Efficiency gains demand reintroducing human agency in supervising computational singularity. And this is how we define contextual AI. So we always welcome collaboration. If you have any interest, idea, or questions, welcome to email us, any of us, and we'll try our best to respond. Thank you so much for listening.